The universe appears to be expanding at an ever-increasing rate, which is one of the most puzzling aspects of modern scientific research. But what causes this rapid growth to occur in the first place? The concept of dark energy refers to an explanation that many physicists feel to be the most feasible. What exactly is the point of it all? And is it possible that there are other possible explanations? The 5 most significant questions and their respective responses. What exactly differentiates dark energy and dark matter from one another? Both of these occurrences have names that include the word dark, but other than that, they have very little in common. Because it is thought to be made up of particles that have not yet been discovered, dark matter is referred to as dark matter. These particles are thought to be subject to the rules of gravity, but they do not exhibit any electromagnetic interaction, such as with light. Therefore, it does not release any radiation, and it continues to be dark. However, this type of matter engages in gravitational interaction with other mass-bearing particles, such as regular matter and photons. These interactions take place. It was found in this manner because dark matter is thought to be the cause of why some galaxies behave in a manner that is not consistent with what is predicted by theoretical models. Fritz Zwicky discovered in 1933 that a galaxy cluster he had been observing could not be held together by visible matter alone. His discovery was groundbreaking for its day. There must be additional material there to account for the fact that the cluster can be held together by gravity. However, to this day, nobody has been able to figure out precisely what causes this peculiar kind of matter in the first place. The behavior of dark energy, which is distinct from the behavior of dark matter yet is just as intriguing, is where the term dark energy comes from. This peculiar sort of energy cannot be directly demonstrated, but it has been shown to hasten the process by which galaxies in the universe drift apart, causing the cosmos to expand forever. Both of these occurrences are responsible for a significant amount of the energy that exists throughout the cosmos. According to some estimates, dark energy accounts for 70% of the total energy, whilst dark matter contributes 25%. Only 5% of the mass comes from normal stuff, which includes things like us, the things in our environment, and the stars. Therefore, we can classify 95% of the cosmos as being in the dark. When and how was the phenomenon of dark energy discovered? Scientists have known for more than a century that cosmic objects that are further from us are receding from us at an ever-increasing rate, and this phenomenon was first identified more than a century ago. Edwin Hubble took measurements of the redshift in star spectra and found that more distant objects had a larger redshift, which corresponds to a higher speed. He concluded that this was evidence that the universe is expanding at a faster rate. Nevertheless, until the end of the 1990s, it was thought that gravity would finally triumph over this dynamic, which would then slow down, stop, and eventually reverse the process of expansion. This assumption lasted until the end of the decade. The discovery that the expansion of the universe is truly speeding was made by 2 study teams led by Saul Perlmutter, Adam Rees, and Brian Schmidt, who used type Ia supernovae as their evidence. The researchers use this particular kind of supernova as a standard candle in their work. It is possible to accurately determine its distance even at great distances due to the fact that its brightness curve is well understood and it emits sufficient light to do so. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Adam Rees, and Brian Schmidt for their discoveries regarding the accelerated expansion. What was lacking was an explanation for the rapid increase that had been observed. The majority of physicists believe that one of 2 explanations for dark energy is more likely. Either it is a product of so-called vacuum energy or it can be explained by an unknown particle and field that travels across the entirety of the universe as quintessence. Quantum mechanics is responsible for the concept of vacuum energy. According to this theory, pairs of matter and antimatter particles are virtual, formed out of nothing all the time, even when there is no matter or antimatter present in the surrounding region. However, the existence of these particles is limited to incredibly brief windows of time before they are destroyed by one another. However, according to one of Einstein's fundamental postulates, mass and energy are interchangeable. Therefore, energy is capable of influencing the force of gravity. In theory, energy can even, in contrast to mass, convey a negative pressure that, rather than attracting mass-loaded things, pushes them away. This happens when the energy is concentrated in a small area. As a result, the expansion of the cosmos may be due to the energy of the virtual particles that exist in the vacuum. Einstein initially included a cosmological constant in the equations that he developed for his general relativity theory, but he later decided to do away with it. This cosmological constant may be used to mathematically characterize dark energy. However, according to the most recent findings of studies, there is a huge energy gap between the vacuum and the considerably smaller quantity of energy that is contained in the rapid expansion. This energy gap can be as big as 120 orders of magnitude. The concept of the Higgs particle is related to the second preferred explanation for this phenomenon. The quintessence idea is predicated on an extremely lightweight and, as of yet, unidentified Higgs relative. This particular particle possesses a field that is capable of penetrating the entirety of space and endowing each point inside it with a quality that is capable of overcoming the pull of gravity. The particle's characteristics would be comparable to those of the Higgs boson, but it would be considerably less massive by 44 orders of magnitude. In contrast to vacuum energy, the impact of the particle or its field would shift throughout the course of some period of time. This would make it possible for the universe to collapse or for all of its components to be torn apart, as well as the possibility of a cold death for a universe in which matter is becoming progressively thinly spread. Are there any other factors that could possibly account for the increased growth? Many physicists believe that the cosmological constant and quintessence are the most likely explanations for the accelerated expansion of the universe. Nevertheless, there is a third possibility that some physicists believe could be the driving force behind the phenomenon known as modified gravity. This viewpoint contends that the general theory of relativity, GR, fails to provide an accurate description of the impact of gravity on extremely vast sizes, which are the kinds of scales one encounters when dealing with the phenomena of space. An alternate explanation could be able to account for the deviations that Einstein's equations are unable to explain. The expansion of the universe is accelerating all the time. Numerous researchers have a hunch that it's due to something called dark energy. Since the measurements of gravitational waves were made, however, the art is more powerful than it has ever been. A modified version of gravity would need to be able to describe all phenomena at least as precisely as the art can, in addition to accounting for the faster expansion. On the other hand, the vast majority of specialists agree that such a theory is not now in sight. How exactly do researchers look into dark energy? Using observations of a wide variety of cosmic objects, scientists are able to measure the accelerated expansion. They construct a motion profile of our surrounds by determining the distances and velocities of the objects in our environment. In addition to that, they make use of the redshift of the objects, which refers to how much the wavelength of the radiation that is released by the objects has changed in the longer wavelengths. It is possible to ascertain the velocity of well-characterized objects, such as standard candles left behind by supernovae Ia. It is possible to determine the distance by measuring the light that is received by the viewing telescope. The Dark Energy Survey is a current large-scale study that is cataloging the biggest fraction of the universe that has been cataloged so far by these categories, DES. A telescope and a customized camera are being utilized by researchers in the Andes of northern Chile in order to record images of 4 distinct cosmological events. These phenomena are supernovae, primordial sound waves, gravitational lenses, and galaxy clusters. In the southern hemisphere, a telescope measuring 4 meters in diameter has started collecting data. The results will become clear in the years to come. We appreciate you watching. Remember to sign up for UpScience's newsletter.